Alright, we're going to flatten out. We're going to deal with Gauss's law eventually. Gauss's law and flat stuff. Fortunately for us, flat stuff is, we're going to use cylindrical sheets to do that. Of course, we all know Gauss's law. E dot dA equals Planck over epsilon naught. And again, we're going to cheat. We're going to choose whatever Gaussian surface we can so that E is uniform across A, and EA is going to equal Planck over epsilon naught. You can see most of the work is choosing A so that E is uniform and getting Planck right. Once you get those two things going, you can get the rest of this relatively easily. And I think you're going to be surprised how easy this part of the proof is. Our first example is going to be a flat sheet of charge. Flat sheet of charge with a surface density that's all we're looking for. So we've got a flat sheet, and we'll even say it's greater than 0, so it's positive. Here's our flat sheet. It's so chock full of pluses. Yowza. Okay, so it is chock full of pluses, and basically it's going to have a surface density across it that's greater than 0 to emphasize that it's the positive. And then it's not 0. I know that's insulting, but still. If you think about it, let's say this thing is from this. Let's turn it on its side, so it's like this. It's going to actually have a field this way, and it's going to have a field this way. It's going to be non-directional, and we should call this. Yep. No, this is good. Okay. So it's going to be very thin. We're going to have an electric field this way. And that actually kind of changes the way that we normally would do it. So the way we will try to solve it is we will we want something that's going to be uniform. We could use a cube if you like, but the cylinder is one that we're familiar with. And actually a cube would work swimmingly. But let's say that we have here's our flat sheet. And we're going to pop a cylinder through that puppy. It goes here to there, and then it goes through to the other side. Okay. So it's got some depth so that it's going in there. And we're going to call the cylinder's width R. And again, we're going to go, again, the nice thing about this is, again, the field's going to come straight out of this puppy. It's going to come straight out of this puppy too. Which means that Planck is going to be pretty easy. It's just going to be the surface charge density times the surface I can spell words. Enclosed by the cylinder. Which is going to be a lot like it sounds. It's just going to be this times 2 pi r. And that's it. No depth there, so it's okay. The thickness is close to 0, so we're going to stick with that. That's going to be Planck. And E dot dA equals Planck over epsilon naught. And EA equals Planck over epsilon naught. Yeah, no. charge density times 2 pi r is going to be E times 2 pi r. But it's going to be a little tricky because we actually have field coming out of both sides. We're actually going to multiply this times 2. I know that sounds kind of weird. Okay. Okay, but that's going to be the way we do it. Okay. Well, I guess technically we're taking this times some thickness t. It's going to be the same for that. But what's going to happen is that we're going to have, oh, this is over epsilon naught. Sorry. So these are going to divide out, and we're going to end up with E equals surface charge density over 2 epsilon naught. And that turns out to be what it is for any flat sheet. If you know the size of the flat sheet, you could always, let's say instead, we knew that the total charge of the sheet was capital positive Q, and that the area of the sheet was L squared, then that would just change this to E equals positive Q over 2 L squared epsilon naught, which again takes a form that we like. Charge divided by some distance squared. So we know the units are going to turn out nicely. Good. The last example, and that's why this part is kind of brief, is going to be between two charge plates, where we go ahead and we so between oppositely charged plates. Well, so we're going to have positive plate again, we're looking at it from the side, and a negative plate. Well, the field is pretty obvious, it's going to be like that. Well, grabbing the center of it is not going to help us at all. We can't just put it in the center, because as you know, if we place our Gaussian surface in the center, blank is going to be 0 and E is going to be 0, which we know is not true. So we have to grab some section of the charge, and what we're going to do is something kind of tricky. We're going to actually take this piece here and we're going to take this as our cylinder, this piece here. And really it could be any piece that's inside the cylinder. It doesn't actually matter. It shouldn't be that big a deal. But you can see it ends up being like, I mean, even by inspection, which is one of the words I hated when professors used it in college, but you can see that this is really just half of this. We're only grabbing the inside or the outside. So it's going to work the same way. We're going to have E times the area, whatever it is the cylinder grabs here, equals the amount of charge that's on the inside of here, which is going to be the surface charge density of the plate times the area over epsilon naught. Now if you look this time, these divide out and we just get E equals surface charge density over epsilon naught. That actually seems pretty fair, because now we're not considering this part here. I mean, if you want to be technical, you actually are grabbing, the way that you're doing it, the reason that it's twice as strong is because you have this extra plate that's also helping you. It's gonna add to the field strength in such a way that you're gonna get this piece here. You're gonna have, it's not gonna be divided by 2 like it was with the flat sheet. That's really about all you need for flat sheets. So enjoy. Go forth and solve, please.